Hello and welcome once again for another ES340 video. This is day 21, example problem 2. So here I have a table that gives a bunch of the properties of the vapor compression system that we're going to analyze. So state 1 gives the pressure, temperature, enthalpy, specific enthalpy and specific entropy, and so on. So we have all of these values rather than having to go look them up on tables or whatever. They're just all given to us. Now, one thing I'm going to note, though, is that I can immediately see that this is not an ideal vapor compression system. How do I know? Because in an ideal vapor compression system, there's one point where it's isentropic, right? Going from 1 to 2, the process 1 to 2 is always isentropic if it's ideal, and obviously going from 1 to 2 here, it's not isentropic, right? There's two different entropy, specific entropy values there. Therefore, this is not operating at the maximum theoretical efficiency that could happen in an ideal vapor compression system. Okay, just making that note. In any case, so data for the steady state operation of a vapor compression refrigeration cycle with refrigerant 134A as the working fluid are given above. The refrigeration capacity is 4.6 tons. Ignoring the heat transfer between the compressor and the surroundings, determine the following. A, the mass flow rate of the refrigerant in kilograms per minute. B, the isentropic compressor efficiency. C, the coefficient of performance. D, the rates of exergy destruction in the compressor and expansion valve, each in kilowatts, and we'll let, for exergy purposes, we'll let the dead state values be T0 equal to, or T naught equal to 21 degrees Celsius and P naught equal to 1 bar. Okay, so for part A, it's pretty simple. Remember that the refrigeration capacity is Q dot in. And we know what the refrigeration capacity was. That was given as 4.6 tons. We also know that Q dot in, if we're ignoring kinetic energy and potential energy effects as usual, we get m dot, and it's in steady state, right? That's how we get an m dot, a single m dot. We get m dot equal to h1 minus h4. So that means that m dot itself has to be equal to Q dot in over h1 minus h4. Now we have a problem here that this is given, the h is given in kilojoules per kilogram, and the Q dot n is given in tons. But in the previous example problem, we noted that 1 ton is equal to 211 kilojoules per minute. So what that means is that we have 4.6 tons times 211 kilojoules per minute per ton divided by what we have, the values that we have on the table here, going from 1 to 4. So here's state 1, here's state 4. We were given 243.3 and 82.9. kilojoules per kilogram, and that comes out to be approximately 6 kilograms per minute. So that's what I'm going to round it to. Now for B, it asks for the isentropic compressor efficiency. So that's assuming that it was isentropic, right? what would we get? It's obviously not isentropic across the compressor, which is state 1 and state 2 in this vapor compression refrigeration cycle. So it's obviously not the case, but then we'll call this state 2s, right? Because that's the what we would have in theory if it was isentropic. So that implies that S2s is equal to S1 is equal to 0.9606 kilojoules per kilogram times Kelvin. Now our working fluid is refrigerant 134A, and we know that we have a pressure of 7 bar. So P2 is equal to 7 bar, and we already know what S2S is. So in that case, if it was isentropic, which we just took care of here, and we have a pressure of 7 bar, we can interpolate. We get H2S, which is equal to 278.06, or approximately speaking, kilojoules per kilogram. Okay, so after we do interpolation, this is table A12, by the way, for refrigerant 134A. And now we have to reach back into our memory banks. Why do I need this? The isentropic efficiency, this was several lectures ago, is going to be equal to H2S minus H1 over H2 minus H1. And fortunately, we don't have to find H2. H2 was actually given to us as 295.13, right? So what we end up getting is we get 278.06. That was what we found by interpolating there, minus 243.4. That was the value given for H1, divided by 295.13 minus 243.4. And this 0.3. These are 0.3s, I think. This gives me approximately 0.67 or 67% efficiency, approximately speaking. For part C, the coefficient of performance is what was asked for. And we know that beta is equal to, well, it's Q in dot over W dot, the net there. Oh, this is the coefficient of performance. Yeah, okay, so that's the net. And the Q in dot is equal to M dot H1 minus H4, as we've already seen. And the WC dot, well, this just comes from the fact that this is exactly what beta is, right? Beta is equal to H1 minus H4 over H2 minus H1 for a vapor compression cycle. We've already been given this in earlier on. And if you plug in those values, obviously the M dots cancel, so you don't have to bother with that. You get about 3.1-ish. Okay, so my coefficient of performance then becomes 3.1. Now the exergy destruction rate in the compressor and expansion valve, that's an interesting piece. So the compressor's going from 1 to 2, and the expansion valve is going from 3 to 4. So what we can do then is we just have to remember that exergy, what is exergy destruction? Well, that was given by sigma dot times T naught, where obviously we know what sigma dot is. So for the compressor, well, now we have to go to the entropy balance equation. Now, I want to make a note of something. We assume that somewhere in here, that there's no heat transfer between the compressor and its surroundings. And we'll also make that assumption for the evaporator as well. Or the expansion valve, excuse me. So if that's the case, then from the entropy balance equation, remember that we have S2 minus S1. That's going to be equal to, we're 0, because it's steady state, is equal to m dot times S2 minus S1 minus sigma dot, and the heat term, which would have been Q dot over T, right? That term, that goes to 0 because we're assuming there's no heat transfer between the compressor and its surroundings, right? So because of that, that term goes away, and what we find is sigma dot is equal to m dot times S2 minus S1. Oh, excuse me, I had this backwards. This is plus, and this should have been the other way around. S1 minus S2. There we go. So because of that, that means that this becomes minus sigma dot equal to m dot S1 minus S2, and then obviously then that implies this, right? So this is how we get to this state. Okay, so now going from there, we can just find this, right? Because we know what m dot is, we found it earlier, and we know what S2 and S1 is. So doing that, what we find is sigma dot is equal to, well, 6 kilograms per minute. And we actually want to get this into, we need to get the units into kilowatts in order to make this come out properly. So, because we were asked for it in kilowatts. So to do that, then we're going to multiply this times, well, we're going to get it to, there's 1 minute and 60 seconds. So the minutes are going to go away. And then we're going to get, there's 1 kilowatt in 1 kilojoule per second, right? Not that we need this final step, but that's just to remind us of that. And then we know that this comes right off the table that was given at the beginning of the problem, the 1.0135 minus 0.9606 kilojoules per kilogram times Kelvin. And once you do all of this workout, what you find is that this is equal to approximately 0.00529 kilowatts per Kelvin, which is not, I guess, too terrible in terms of the sigma dot. And that means that our E our ED, our EXD dot is equal to, well, remember we were given T naught as 21 degrees Celsius, so that's the same as 294 Kelvin times the 0.00529 kilowatts per Kelvin. And that's going to be approximately equal to 1.56 kilowatts. So that's going to be my exergy destruction rate for the compressor. For the expansion valve, it's a similar process. During the expansion part, again, that's the process 3 to 4. So this is just going to be T naught times H4 minus times M dot, times H4 minus H1. And if you put all of that information in, what you should find is that this ends up being approximately 0.553 kilowatt. Okay? That's all that I have for this video. Hope to see you again soon.